Yeah, can you hear me? Hello? So hello guys, yesterday we had the walkway simulation of the GPS module. Today we are going to be seeing the final hardware and software part of the circuit, that if you have the necessary materials that you can make on your own at your house. So let's start the session. Today we are going to be talking about transmitting data from our tracker circuit to receiver circuit. Initially our MCU will be in a low power state, and as soon as it detects some power, as you know, it detects a movement through the accelerometer. The accelerometer sends an interrupt signal to the MCU to make it power up the GPS module. So it starts getting the coordinates, which we then transmit to the receiver module through LoRa. It starts this tracking loop where it continuously does the same thing. Then after it has stopped, again the accelerometer shows that it is not moving. So the MCU will record the coordinates one last time and put the MCU back into sleep mode. So in our tracker circuit, we are going to be using GPS module, LoRa transmitter, motion sensor, microcontroller, and battery power. For the receiver circuit, we are only going to be using LoRa receiver and microcontroller. So this is how the data will be flowing in our GPS module. First, the LoRa transmits the transmitter LoRa takes the coordinates from the GPS module, converts it into radio signals, and then send it to the receiver LoRa, which then sends it to the MCU of the receiver circuit, which processes the data and sends it to MQTT protocol, which can make us see the coordinates on the live dashboard. So about LoRa
Yes, I hear you. Yes.
Yes, sorry guys, I had some issue with my Wi-Fi. So let's continue. And LoRa is used for uh, long distance communication that sends data wirelessly through radio signals. This specifically designed for low power devices and can transmit data over 10 to 20-kilometer range. The reason we are using LoRa or Wi-Fi or cellular is due to because Wi-Fi is first of all short range and cellular you have to pay for it. Well, this is completely free. LoRa is also used has many application in IoT and remote monitoring systems. So let's talk about how LoRa works. First, the coordinates are sent to LoRa, transmitter LoRa, which is digital data, which is then converted into radio signals, travels to our receiver circuit. The receiver reconstructs the original data through the help of the microcontroller, and then we send it to MQTT to get our coordinates. This is since we are only going to be sending our coordinates, it's low data rate. It has very low baud rate or bit rate. So here LoRa is optimal for it. So yeah, this is why LoRa is useful in our project compared to other means of data transportation. This is going to be the LoRa module we are using. As you can see, we have to connect these pins as per our requirement. Let's go through the pins right now. VCC and ground are power connections. The ANT pin is antenna pin, which helps in the data transmission. The MOSA and MISO pins are there to exchange information between the LoRa module and the MCU. Like suppose the MCU has to give data from GPS to LoRa, it sends it through MOSA pin, and if LoRa has to say something back to the MCU, then it says it through the MISO pin. So we have the serial clock pin. This is made to synchronize the data exchange between LoRa and the MCU. The NSS pin is used because there can be like one MCU which is connected to multiple LoRa modules or slave networks, and we use NSS to make sure that only the correct slave is using the information. So the MCU turns NSS's low of the specific slave used, then the slave uses the information. Meanwhile, the other slaves ignore the information. The RST pin is made to reset the module, and the DIO pins we are using for interrupt function, so that if there's an issue with the LoRa, it has to say that it has finished transmitting. It sends an interrupt signal through the DIO pin to the MCU. We are going to be using DIO0 for our circuit because it's pretty simple circuit. The other DIO are usually used in advanced LoRa. So the components we are going to be using for our circuit are the accelerometer, the MOSFET, the LoRa module, GPS module, and ESP32. This is for the tracker circuit. For receiver circuit, we are going to be only using the LoRa module and ESP32. So yeah, MOSFET is a transistor which acts as a semiconductor switch which is voltage controlled. You see it has three gates: gate, drain and source. In a P channel MOSFET, when the voltage difference between source and gate is greater than V threshold and V source should be greater than V gate, then it connects the drain pin to the source pin, so current flows from drain to source, or source to drain, my bad, sorry. And for an N-channel MOSFET, here V gate should be greater than V source and VGS, the difference between VG and VS should be greater than threshold voltage. If the condition is satisfied, then again the connection is established and current flows from drain to source. You see there are some differences between N channel and P channel type. First of all, the main difference between them is their activation condition. Next, for the N channel MOSFET, it can handle more current and it is faster in switching. Whereas for P channel MOSFET, it is easy to control and used for high side switching. Suppose you take a H bridge, which is, let's take an example of H bridge. Here you have the main power source. Load. Where each of these switches is a MOSFET. So if you close 1 and 4 switches, we have current flowing in this direction. And if you close 2 and 3 switches, then we have current flowing in this direction. So this circuit is made to change the direction of current through a load. Let us see how we are going to be using MOSFETs here. So the MOSFET's drain is connected to here and source is connected to here for switch 1. And here will be the gate. Similarly, it's like similar. You put a mirror through the middle, then it will be like similar circuit. So we will be talking about 1 and 3 switches. Again, you're going to be connecting drain of switch 3, source of switch 3, and gate here. So these two are going to be P channel MOSFETs. These two are going to be N channel MOSFETs. For it to work, we need to make sure that VGS is greater than threshold. So for this to open, we use the MCU to send some power through it. So we get VGS to be greater than some V threshold, which is like approximately 4 volts or 5 volts. And the source voltage is going to be here VCC, where since this is open currently, this will be ground here, so 0 voltage currently. So when we supply voltage to this switch closes and current flows in this direction. And if you go to the N channel MOSFETs, the source is at ground potential, and if we use the MCU to send some voltage to the G pin so that VGS is greater than again threshold and current flows from drain to source. So using MCU, if we switch on S1 and S4, then current flows in one direction. Similarly, MCU, again we use the MCU to switch the current direction using switch 2 and 3. This is one of the many uses of MOSFETs. MOSFETs are also used for charging and discharging circuits where if the voltage, like suppose you want to charge a battery to 4 volts, you connect this MOSFET in such a way that when 4 volts is received, then the MOSFET closes itself using the MOSFETs, like MOSFET's property. And similarly for discharging circuit also, suppose you want it to only discharge till 2 volts, you make the circuit such that if it goes below 2 volts, the switch opens again. Without using an MCU, it's like directly based on the battery voltage itself. Yeah, now let's go to the next slide. This is the receiver circuit. Now let's talk about the connections in the transmitter circuit. First of all, we can see that all the grounds are connected to the ESP32. Next, first let's talk about the accelerometer. You see this INT1 pin, this is the interrupt pin. When accelerometer detects movement, the INT1 pin sends a signal to the ESP32's pin, 33 pin here, to make it wake up from its deep sleep state. And then the ESP32 has some other functions like waking up the GNSS and configuring the LoRa and stuff. We'll talk about that later. First, let's talk about the accelerometer. You see CS pin here is set to 3.3 volts. This is to make sure that it's set to a certain state. You can set it to 5 volts also, but then it will be working in a slightly different manner. We are going to be setting it to 3.3 volts for our use case. You can see that we are using 3.3 volts for all the components in our transmitter circuit. Next, let's talk about SDA and SCA. SCL and SDA are part of I2C communication protocol. These are used to transmit data between the accelerometer and the ESP32. SCL is serial clock line. It synchronizes it with the ESP32. And SDA sends the data between ESP32 and accelerometer. It works in both ways, like you can send data from accelerometer to ESP32 and from ESP32 back to accelerometer. So yeah, now let's go to the LoRa module. You see the NSS pin is connected to one of the digital pins of ESP32. When we want the LoRa module to receive data from ESP32, we turn it low, so it can send data through the MOSI pin, which is also connected to one of the digital pins of ESP32. The MISO pin, as we talked before, is what transmits data from the LoRa module to ESP32, and is also connected to one of the data pins of the digital pins of the ESP32. The serial clock pin is also a digital data, so it's also connected to a digital pin. As you can see here, the DI-0 is connected to ESP32. This is also used for interrupting the ESP32. The interrupt basically works in such a way that suppose ESP32 has multiple functions, not only maintaining the circuit. So whenever the interrupt signal comes, it stops all other functions and takes a look at the interrupt signal and its related functions. So yeah, the reason we are using MOSFET in the circuit is because the GPS module, if you keep it always on, it takes too much power from the circuit. So since we are making a low power model, we are going to be using a MOSFET such that whenever we want it to be powered on, the MCU will, I will talk about the settings later, but the MCU will be switching on the MOSFET, so current goes to the GPS module. As you can see here, the gate is connected to a pull-up resistor, which basically means that in the default condition, the gate is set to high digital value, and this is a p-channel MOSFET. So whenever the MCU puts the gate to low value through pin 26, then the MOSFET will be switched on. Volts, and the drain is connected to 3.3 volts of the GNSS module. Since initially both are at 3.3 volts, there will be no current. And whenever the accelerometer gives interrupt signal to ESP32, then it will also, the ESP32 will also make the gate to logic level low. So it will be at 0 volts. Because of the difference between the voltage, the current goes through to GNSS module. Now let's look at the GNS module pins. TX and RX are pins are used to communicate with the ESP32, like the transmitter and receiver pins. And this thing is the antenna with which it uses to communicate with the satellites to get its coordinates, which then goes through the TX pin to ESP32, which through the lower module goes to the receiver circuit. This is similar to the tracker circuit, but the only difference is that there are no other components, so we're going to skip that. Now Anand is going to continue with the software part of this.
So guys, just give me 2 minutes. I'm setting up my the background and everything. Just give me 2 minutes. Yeah, guys, I hope you can see the screen now. So yeah, just give me some time. So yeah, so since we are done with the hardware architecture, I hope you can listen me. Since we are done with the hardware architecture, and let's now explore the firmware design. So why this firmware is important and like why we are doing this. So I want to teach this with a small example. Okay. So now we assembled each and every components, right? So we assembled every component and yeah, we are done with that. But now we should implement some tasks like we need to track the GPS data. We need to take the GPS data from GPS tracker and send it to the receiver node. For doing that, this MCU is not, I mean, this MCU won't do it automatically because it is not having any intelligence. Okay. So instead, what we will do is, I mean, what we need to do is we need to tell the MCU that what to do because MCU is not having any intelligence like humans. So we will tell that through a language which we call some like C++ or C, embedded C++, embedded C, programming language. So we will do that with this, and Now we'll be exploring two different nodes in this project. One is tracker node, sorry, three different nodes in this project. So first is tracker node, second one is receiver node, third one is your dashboard. We will create a dashboard to represent everything. Okay, so let's start. And yeah, let's start this. So the first thing is uh, like in the project, like in the firmware design which we are going to do now, like which we discuss now, we use something known as libraries. So a library is nothing but it's a collection of pre-written code that provides reusable functionality. And most embedded libraries express classes, allowing developers to interact with hardware through objects and numbers functions. So there will be some libraries provided for C, like in C++. So what that library will do is it will provide some classes and objects with some functions to manipulate some data. So what is class? Class is nothing but creating a new data type. Okay, creating a new data type. So like int is a data type, float is a data type. Likewise, you can create custom data types using this class. Okay, so like for example, you want to store data of some cars. So every car will be having its company name, its name, like Fortuner. Fortuner is its name. Its company is Toyota. It's having some engine specifications and all, right? So likewise, I mean, if you want to store that data in a structured way, you should use this classes and objects function, like classes and objects concepts. So how we'll do that? So this library will provide you some classes, and you will assign a name for it, like int x, right? Int x. So x is the name for a variable. Likewise, you will name it, and it will ask for, like, it will be having some attributes or some characteristics. We will also we also give that information, and these libraries will provide you some functions to manipulate. So for example, GPS tracker, it will send the data. The output of GPS tracker is through NMA sentences. We call that as NMA sentences, which is really clumsy. So to process this data, we use a library known as tiny GPS. So it will have some functions in it to process that. Okay, so think of it in that term. And so we will create our firmware design in this way for three different nodes. So first we'll define constants, include libraries, create objects, create some functions. Then we will go for void setup and void loop. Okay. Uh, Tracker node. So I want to give a small brief about this tracker node before going into the firmware. So yeah, this is your tracker node. We haven't included a battery and switch here, but just imagine you are having, like, we will power everything. We will give power to ESP32. We also include one switch. So first, when you turn on the switch, what will happen? Your ESP32 will be waken up. Like, it will wake up. It will implement void setup and void loop and everything. So since, like, the logic inside the, like, firmware will tell you to go to deep sleep. Okay. So your ESP32 is in deep sleep. Your ESP32 is in this ESP32 in deep sleep. Okay. And now what accelerometer will do? It is having this int1 pin, right? This int1 pin. This int1 pin will wake up your ESP32. And we should tell the ESP32 that if this pin goes high, then only you should wake up. We should implement that logic. We should tell it in we should tell that in its own language. Okay. And after ESP32 wakes up, we need to turn on the GPS. I mean, we should make this gate to become low. Okay. Uh, Wait a minute. Sorry. So we should make this gate pin to become low. Then only it will power on the GPS, and that GPS will receive the information from satellites. It will convert it into NMA sentences and process it to GPS. And the problem with GPS is when it gets turned on, the GPS will take some time to fix. I mean, it won't give you the correct output right from the starting. It will take some time. Okay, uh, it generally takes some time, and we need to wait until that. So we should tell the GPS. So you should wait for some time. We'll call that as GPS fix. Okay, GPS fix. And after we receive the correct NMES sentences, we need to process that, and we need to encode that into some structured format so that LoRa can transmit it. We should tell the ESP32 to do that, and it will send it to the LoRa. Okay, the LoRa will transmit it. So this is how we are going to do our circuit. And our circuit, I'll tell you some information about our circuit, what it does. So accelerometer will wake up when it will detect the motion and it will wake up. So this will detect the motion and it will wake up. And the second thing is uh, ESP32 will power on your GPS, and this tracker node will send the GPS coordinates to the receiver base station for every 60 seconds. And it will send the start packet. When it gets started, like when it detected motion, it will send the start packet. And if the motion is still continuing, it will send one GPS packet for every 60 seconds. And it will also send when the motion is stopped, when the accelerometer will tell that motion is stopped, it will send the stop packet, so the final packet. So this is the workflow of this tracker node. We will just explore more into this. You will understand eventually. Don't worry. Yeah, tracker node. So the tracker node is this, and yeah. So I will just go through these libraries first, what they provide. So this is the foremost basic library which you will use. Hashtag include Arduino.h. Okay. So it will provide you the fundamental functions of the ESP32, and this include wire.h. This will provide you I2C communication between ESP32 and accelerometer. And this SPI.h will use it to establish SPI connections between ESP32 and your LoRa. And for UART connection between connection between GPS and your MCU, we'll be using that functions are included in this Arduino.h only, so don't worry about it. And this is Sparkfun LIGDH, which is used for accelerometer processing. And we have Tiny GPS, which is used to process the GPS information and all, like the NMES integers, which is provided by the GPS module. And this Arduino.json.h is used to format the data to send into LoRa. This is used for processing the LoRa information. Okay. So as I said, first we will define the libraries, then we will define some pins, like what these pins do. So the first thing is we'll defining these pins of ESP32, pin number 21, 22, 23, 33. So this pin 21, 22 handles standard I2C data. So it will I2C data between your ESP32 and your accelerometer. Okay. And pin 33 is an RTC capable line that wakes CPU from deep sleep. So this into one pin is capable. This is this will wake up your ESP32. Okay. And GPS telemetry link. So these pins are used for GPS telemetry link. Pin 16 and 17 establish dedicated hardware serial link between your GPS module. The name of the GPS module is Max M10S, and it will also do parsing data packets and standard 9600 baud rate. I hope you all know about what baud rate is. And these pins are for LoRa, the connection between LoRa and your ESP32. Okay. These GPIO pins establish the complete hardware interface between ESP32 and the SX1276 LoRa module. That's it about this. I included some information in this for your reference. And this pin is to control the gate pin of MOSFET. Okay, this pin will manage the power to your GPS module. When this pin goes low, like when GPIO 25 is assigned to control the MOSFET gate, that powers the GPS module. By driving this pin low or high, the ESP32 can switch the GPS module on or off. The main purpose of using this MOSFET is our GPS will consume a lot of power, so we are restricting that with the MOSFET. Okay. And these are some constants. So I'm defining this constant for further, like this. You will understand this later. I'll just skip this part right now. You'll understand this later. And these are some LoRa frequencies. So I mean LoRa peripherals. So the first thing is LoRa frequency. So you are defining the LoRa frequency to 433 megahertz. So this is unlicensed frequency, like unlicensed frequency. You can, like anyone can use this frequency. There is no restrictions on this. And then you are having bandwidth 125 kilohertz, and this is LoRa spreading factor. So we call this a LoRa spreading factor, and we assign 9. So what is the spreading factor is? Like it will determine how speed and how long your data should transfer. So if you're having less spreading factor means then your data will be transferred faster and the distance will be less. And if you are using a higher value, then your data will transmit for higher distances but with less speed. And coding rate is this is being used for some error detection purposes. Just leave this part. And LoRa TX power. So this pin, like we assign this to 17. Like how with how much power your antenna should transfer the data. So this is the optimal value. We'll use that. And then this, like this LIS3DH is the class of this library. It's a class belongs to this library, and we are defining an object. I mean, the name of our accelerometer is IMU, and we are establishing the connection between, like we are telling the connection protocol between accelerometer and ESP32. It is a node with the address 0x18. Okay, and you are creating an object tiny GPS plus GPS. So this is the name of your GPS, and the UART protocol will use GPS serial 2. This is like every ESP32 will be having three connections, three UART connection protocols. UART 0, UART 1, UART 2, and we are using the second one. Okay, so like the third one, 0, 1, 2, we are using the third one, 2. And this SX1276. This is like establishing the connection between LoRa and all. And RTC data adder will take up from motion. So I will leave this part for right now. You will understand this later. And yeah. And the other thing which I want to tell you is, so like just now I, like in the group I posted some source codes. Just open that file. It will be very much useful for this. Like it will be very much useful. Like just open that, because in the today's session we are not focusing much on the syntax part, because like the source codes are really huge and we cannot discuss everything. Like the syntax also, I mean really the syntax is vague, so we'll be understanding the logic part only. So yes, I'll start with these functions. So we are using some functions inside this tracker node. First I'll discuss about those functions. So the first function which we'll be using is, like which I defined is void GPS on. So like void means your function won't return anything. Okay, void GPS on. So after calling this function, what will happen? So you call this function. This will set the GPS power control pin to low. I mean, this will set the MOSFET gate pin to low, so that MOSFET will turn on. GPS module will receive power, and it will wait for 10 milliseconds, a very short period of time, and print GPS powered on end. So it will come out from the function. So that, like this function will turn on your GPS and void GPS off. Similar to this, but reverse. Start, set GPS power control pin high, like MOSFET will be turned off, and GPS power will be disconnected, and it will print this. So this printing is for our purpose, okay? Like for decoding, like for observing what happening in our circuit. We print these things generally. And this is another function. Wait a minute, better I'll just open this code sideways. Better to do that. Wait a minute. Just give me a minute. I hope you can see the screen right. On the left side, I'm having the code. So these all are pins, and yeah, this is our void GPS on function. I hope you can see that, and this is your void GPS off function, and this is bool setup LISDH function. So I'll tell you what is this. So after calling this function, what it does. So it will take care of like whether our accelerometer is turned on or not. When you turn on this, when you call this function, it will take care that whether the sensor accelerometer is the communication between accelerometer is between accelerometer and ESP32 is working or not. And after that, it will set that sampling rate to 10 kilohertz. These are some internal connections, like internal settings that we should keep to the ESP30. So sorry, the accelerometer. We'll set the sampling rate to 10 kilohertz and set the measurement range. So this is nothing but your sensitivity, sensitivity of accelerometer. Then you will apply these settings to the sensor. You will set the motion threshold, set the motion duration, enable motion detection on XYZ axis. These are some internal connections, and we will enable the interrupt output so that ESP32 will be notified when there is motion detected through int1 pin. This will be done through int1 pin, and we'll enable the last interrupt mode. So what is this last interrupt mode? Uh, for example, your target is moving. Your target is moving, and accelerometer detected as the high. So I mean, it detected motion, and int1 pin goes high, right? And like it won't stay for long time. Like if you don't enable this latched interrupt mode, that high won't stay for long time. Okay, to stay that for long time, we are using this enable latch interrupt mode so that ESP32 can detect the motion. It won't miss anything. Okay, then so I kept some syntax here, like for your reference, I kept all the syntax used in that function. I also told like which library it belongs to and the purpose of those things. And next we are having this void clear LISDH interrupt pin. So what it does? So last time we like in the last function we entered into the latched interrupt mode, but it shouldn't stay for a long time, right? Like any other situation came, for example, the motion stopped, then it should remove this, right? Some other like the int1 pin should go low. If it is in latched interrupt mode, then it will stay high forever, right? We need to clear this. So for doing that, we use this function void clear LISDH interrupt. So I'll tell you what happened. This is a small workflow that will explain. Motion detected. So the LISD sensor detects the motion exceeding the threshold. Interrupt generated. The sensor sends the signal the, to the ESP30 to notify it of the event. Then interrupt latched. So your interrupt got latched, and when you read that interrupt register, that will be cleared. So we just read that, okay? And sensor clears interrupt. Yeah, that's it. System waits. The system prepares to detect the next motion event. And this is other function bool is motion detected. Whether the motion is detected or not, this function will check that. So how it will check that? So it will first check your int1 pin. If int1 pin is high, then it is detected as like motion is detected, like there is motion. If the int1 pin is low, then no motion detected. Simple function. I'll show you the code for this. It's pretty small. Yeah, this is your void clear LISDH interrupt, and this is bool is motion detected. And the next thing is this function bool wait for GPS fix. Okay, this is a pretty simple function. So it checks whether the GPS data, like after turning on your GPS, whether the GPS data is correct or not. I mean, So like initially I told you, right? The GPS will take some time to send the correct NMA sentences. So this will check whether it is sending the correct GPS, I mean, correct NMA sentences or not. So when you call this function, it will print your GPS waiting for fix, and it will initialize the timer. Okay, this millis is nothing but, okay, just leave the syntax for now. So it will initialize the timer and check timeout. Like there will be a timeout ms. So I'll tell you what is this timeout ms. Timeout ms is nothing but uh, like if this time is exceeded, just get out from this GPS fix. I mean, there is a, like this timeout ms is 1.5 seconds. Like if this millis minus start is, you know, greater than 1.5 ms, just come out from the loop, because we don't want our GPS fix to continue infinitely, like for a long time. It will waste our, it is not having any use. Okay, so we will check this, like has millis minus start reached timeout ms. If it reached, we will exit the loop, and if it is not reached, so we will do this: read and decode GPS data. We'll decode the GPS data. I mean, if the timeout is not reached, we'll check the valid fix. This is the logic behind checking the whether the information is correct or not. We'll check whether the next NMA sentence is ready. This is some inbuilt. The second GPS location is valid is an inbuilt algorithm. So just consider it as an algorithm to check whether the GPS is correct or not. If yes, then we'll print this, and if no, we will just exit from the loop. So this function is basically for checking the right enemy sentences is there or not. Okay. And this is some syntax, like I kept it here. Then we have read GPS data. So this function, like when you call this function, it like it reads for the NMEA packets. It will check the validity. It's an inbuilt algorithm provided by the tiny GPS module, like tiny GPS library. If the location is invalid, it will just return false. If it is correct, then it will read the latitude, it will read the longitude, it read the speed, check the date and time, create unknown. Like if the date and time is not available, like sometimes it might be corrupted. And date and time is not that important, right? Like we are doing live tracking, right? So the date and time is not much important. So if it is not available, then we just keep it as unknown. We create an ISO timestamp. This is the standard format for transferring this thing, and return true. If all data is successfully prepared, just return true, and end of this read GPS data function and some syntax of that. Then we have string build LoRa packet. So we are done. Like we have NMA sentences now. So and that NMA sentences are valid, and we processed. I mean, we extracted that information. Now we should format that information. Okay. So this is the process for formatting that. First, like we receive the GPS information, we'll create a JSON object. I mean, we'll create a small file inside our code, like inside the computer. It's a very small, like I guess 200 bytes, very small thing. And we add our device ID, the name of our device. We'll add latitude that to that file, longitude that file, speed, like all the information, and also the device status. So what is this device status? So like is our vehicle is moving or stopped or started, just started. So that information, we'll also include that information, and we'll convert that to a string, because our LoRa cannot send a file. Okay, it will send bit by bit. So we'll convert into a string so that our LoRa module can send that, and we'll return this LoRa packet. Okay, then we'll having this bool send LoRa packet function. So what it does? So now we are having the data packet ready. It will display the packet for our reference, like in the screen using serial communication. It will prepare for LoRa. I mean that like it will prepare for transmission. So the transmission will be started now. It will determine the packet size also, like how much data is like we are transferring. This will be used for error purposes. I mean, if there is any error happen, we can track that. If any bits missed in between, then we can track that. If we give this information, we can track that, and we'll just transmit that packet. And there are some algorithms inside LoRa module to check whether the transmission is successful or not. So if it is successful, it will display the result successful. If it is a failure, then it will display the result failure. Okay, that is the logic behind this rules and LoRa packet. And void send the stop packet. So for example, our accelerometer detected the motion is stopped. Then what will happen? So motion has stopped. Read the latest GPS information, the final GPS information. Create a LoRa packet with status stop. Okay, and like it will create the LoRa packet using this string build LoRa packet function only, and then it will display the motion stopped, sending a stop packet. And after that, like it will also check whether the data is valid or not. Then it will just transmit it. Okay, it's a pretty simple function. And then we are having this void go to deep sleep. So this is actually, so like if the motion is stopped now, like our accelerometer detected as motion is stopped, and we should tell the ESP32 to go to deep sleep mode, because we need to save battery, like the energy, right? So for that purpose, we will send the ESP32 back to deep sleep mode. So we'll just prepare ESP32, like it will print preparing for deep sleep mode. It will clear the accelerometer interrupter, like the into one pins value, and configure wake source, like whom should wake up the MCU. Okay, we will give that information also. The accelerometers into one pin should wake up, like wake that. When this into one pin goes high, it should wake up. Okay, and it will enter into deep sleep mode. Yeah, done. And what is this wake up event? So like when the motion is detected, like accelerometer sets the into one pin to high, the ESP value will wake up automatically. We configured that before only, right? We did that here. And I also included some syntax that is useful. So this is the tracking loop. I'll discuss about this later. Okay, give me some time. We'll directly go to void setup and void loop, then come back to this tracking loop. So void setup. So what happens in this void setup? So first, okay, I'll just show you the code sideways also. Yeah, void setup. Wait a minute. Yeah, this. So yeah, this is your void setup. You can see this here. So first of all, we'll begin our serial communication. I hope you can see that here. Then we'll use boot counter. So boot counter is nothing but it's for our reference, I mean, for debugging purpose. So it will show how many times the ESP32 waked up and doing its work. How many times the ESP32 waked up. So it will take care of that. And after, like just after waking up from the deep sleep mode, it will turn off the GPS module for saving your energy. And it will initialize I2C communication between accelerometer and ESP32. Then it will initialize your LoRa module, will determine the wake up reason. So what made your ESP32 to wake up? It will also determine that also. It will check for the motion. If the motion is still continuing, it will turn on your GPS. It will start GPS communication. We'll wait for GPS fix. Like these all are functions. I hope you can understand that. We already made the functions for that. You can see that here, all the logics in the code. But since that syntax is, it will take some time to understand. We use these flowcharts to explain it much more efficiently. Wait for GPS fix. read the GPS information, create the start packet, and transmit the start packet. And then we will enter into a tracking loop. So what is this tracking loop? So I'll just go back here. Just remove this. Yeah. So tracking loop. So what this tracking loop does? So even after sending the start packet, the motion is still detected. So what it does? So first of all, it will check whether the motion is detected or not. Okay. So first it will check for whether the motion is detected or not. If the motion is detected, then there is no motion variable that will check, like if the no motion count and the no motion variable become 3 times, like the motion detected, if the motion is not detected for 3 continuous times, then we will detect that as uh, like motion, like the target is stopped. Okay. So just I want to tell that. And if the motion is detected, yes, and it will go to your, or what to say, this loop. I'll tell about that. If the motion is stopped, then it will send the stop packet. We already discussed this function, like stop packet. And if the motion detection is still happening, it will come back here. So what it does, so basically what it does is it will send a packet for every 60 seconds. That's it, simple. It will send a packet for every 60 seconds. So it will use this some logic for doing that. So last send time is millis, and it will, sorry, sorry, here I started it somewhere else. So millis minus last send time is, it is greater than or equal to track interval ms. This track interval ms is 60 seconds. If this like this logic became bigger than 60 seconds, then read the GPS data, build the packet, send via LoRa, and packet sent. If this is less than 60 seconds, then skip the cycle. So it is nothing but you are sending a LoRa GPS packet, a LoRa packet for every 60 seconds. Okay. And if the motion is detected, like after, like in between, if the motion is detected as no, the motion has stopped, then what it does is it just exits the loop. It will turn off your GPS. It will directly go to deep sleep mode. Okay. And your device is turned up, and it will wait for another accelerometer motion. Okay. Like it will wait for the accelerometer's instructions to wake up or not. If again the accelerometer detected its motion, then ESP detector will again wake up and do everything. Okay. And void loop, like in this, wait a minute, I'll just, okay, give me, I'll stop presentation for 1 minute. Just give me some time. I hope you can see the screen now. So the void loop is nothing, like we intentionally left it empty because there is no, like there is no use with void loop here. But we need to write void loop, otherwise the like the code editor will give an error. I mean, that is the structure. So we should include void loop definitely. And if somehow the code reaches here, like it won't reach, but if somehow it reaches here, it will just go to deep sleep. Okay. That is the logic behind the tracker node. We will just come back to the presentation slides, and then about receiver node. So then now receiver node will do two things. Okay. It will receive the information through LoRa from the tracker node. It will process that information and send it to the MQTT broker through Wi-Fi. Okay. We will explore that now. So the libraries which we are going to use is this. We already discussed about Arduino.h, SPI.h, Radio Arduino JSON. The two more libraries, I think you are familiar with this because these have been told in the session 4, Wi-Fi.h and pubsubclient.h. But this Wi-Fi.h is used to connect connect ESP32 to your Wi-Fi, the Wi-Fi connection, and this PubSub client is this. I mean, this library is used to maintain, like, used to connect the MQTT connection. I mean, used to connect to your MQTT broker. Okay, basically enabling the ESP32 to publish and subscribe the messages through an MQTT broker. Okay, simple. And these are pins which we are defining inside it. We already discussed about this, right, in the last track and all part, and also peripherals. We also discussed this. The extra pins which we are going to use is, like, we will have the username and password of our Wi-Fi. We will include that inside it. I hope you can see this. Your Wi-Fi is slide in your. This is your Wi-Fi. Okay, you should change this, and you have this MQTT broker. So we need to store the information of MQTT broker. So we are using HiveMQ, this broker, with this code 18883, and the MQTT client ID. I mean, the ID is ESP32 receiver 01. And since it's a free version, there won't be any password and user and password. Just leave that. And our topic name is GPS tracker. So like a topic is nothing but since many people are using this free version, I mean the same broker and same code. So we have our own topic, okay? So this topic, like whoever, like we will send our information to the topic, okay? We'll send this information in the name of topic to the MQTT broker, and whoever subscribes to this topic, whoever want data from this topic will listen that. Think of it in that way. And these are some variables to establish the delay between Wi-Fi reconnection attempts. Otherwise, there will be a problem, like the Wi-Fi will try to reconnect infinite times in between. So to avoid that, we have this 5-second delay part. And yeah, this is for establishing like the LoRa. And this is okay. This Wi-Fi client is nothing but it's the name of your Wi-Fi. Okay, this is the name of your Wi-Fi, and the name of your MQTT. The MQTT broker or the MQTT thing is MQTT, and you are using this Wi-Fi to transfer that data to MQTT broker. Okay, I mentioned that here, and this is a LoRa packet received flag. You will get to know more about this later. We'll discuss that. And this is a function. When you call this function, it will make this LoRa packet received to true. Okay, we'll discuss. You will understand this later. And we'll come back to this functions part. The functions which we are going to use in receiver mode is, like, the first two functions are void connect and connect to Wi-Fi, maintain Wi-Fi. These are two important, right? We need to connect to Wi-Fi. We also need to maintain that Wi-Fi. So how we will connect to Wi-Fi? First, we'll check for the connection, whether Wi-Fi is already connected or not. If connected, we'll just leave. If not, then set mode. So set mode is nothing but in this mode, it will detect Wi-Fi connections. So what all available in its area, it will detect that. And then you will begin the connection. So you will enter your Wi-Fi password and username, and you will begin the connection. Wait for the connection to be established. After the connection established, you will just display the IP address on your screen and maintain Wi-Fi. So first of all, it will check for the connection status. If it is connected, then it will just come out from the function. If it is not connected, then it will wait for 5 seconds, and it will again try to reconnect. Okay, that is what it does. It just try to maintain the Wi-Fi. Simple function. That's it. And yeah, connect MQTT. So I mentioned some syntax here, so it will be useful for you guys to understand later. And connect MQTT. So what this does, it will establish connection, like the MQTT connections between your broker and your receiver node. Okay, it's a simple thing. So first, after calling this function, it will just print this, and it will attempt an MQTT connection. If the connection is successful, print connected, return true. It will return true. If not, it will just give an error, like there's some error is happened, and it will print us like print failed, and it will return false. Okay, and I included some information, some helpful information here. Okay, I'll just go through this and maintain MQTT. So this function, like likewise maintain Wi-Fi. This is another function for maintaining your MQTT. Okay. So after entering to the function, it will check whether MQTT is connected or not. If it is connected, then it will enter into this MQTT loop. So what this MQTT loop does? So it will handle, like, it will make this MQTT connections live. I mean, always turned on. If somehow the connection is failed between you and your MQTT broker, then it will try to reconnect that using this logic. So we'll wait for some time. If that time is exceeded, which is 5 seconds, it will do another attempt. Okay, using the broker name and all those things. So I included that here. What this function does, let's check for MQTT is connected or not. If it disconnects, try to reconnect only after a minimum interval. And if it is connected, it keeps the connection alive through this function. And yeah, this is all about this function. And you have another function known as publish location. So you will receive that LoRa data, right? And this function will receive the data and prepare that data to publish to the MQTT broker. It will say, this function will send the the received data from LoRa to the I mean MQTT broker. Okay, it will add some other information, I mean device ID and location. It will add each and every information, make it into a structured format, and send it to the MQTT broker. And if it is published, I mean the publish is successful, then it will log a message like success. Otherwise, it will send an error message. That's it, simple. Then we are having this handle LoRa packet. So this function will make sure that, like, when you call this function, it will take the data, like it will receive the data. Okay, so I'll just explain it through the logic here. I'll give you some time. So first, like after you call this function, it will wait. I mean, it will start listening. So it will try to listen the packet and the air. I mean, your receiver. So your tracker will send all the data right through LoRa, and this function will receive that data. Okay. So if the packet is received successfully, then it will follow this. Otherwise, it will discard the packet and come out from the loop. And if the a packet is received, then it will show the packet details inside your screen on the screen for debugging purposes, and it will extract the GPS information. It will validate the required fields. I mean, it will check whether the information is correct or not. If anything, like, is there anything missed in between or not? And if nothing is missed, then it will uh, read the tracker, create a new data packet, like a copy all the GPS like into the receiver node. It will add signal and metadata, prepare MQTT payload, publish to the MQTT broker. Okay, so it use this previous function. Sorry, we'll use this publish location function to this part. Wait a minute, I'll show you the code for that. So yeah, this is your handle LoRa packet. So when you call this function, first of all, it will like it will read the data, incoming data, it will check for some errors, and finally it will make it into a structured format, and it will send that data to the like it will publish to the MQTT broker. Okay, publish the device ID and all the data to the MQTT broker. that function will do that. And this is your void setup. I'll discuss about that. And I also included some like the syntax here. I can go through this. So void setup, what this void setup do? So when you call like when this void setup is started, so it will initialize the serial communication so that we can see all the debugging messages on the screen. It will connect to Wi-Fi. If the Wi-Fi is not connected, it will try to retry this Wi-Fi connection. If the connection is successful, then it will try to connect MQTT broker, and then it will initialize the LoRa like LoRa module. The LoRa initialization is successful. So there is some algorithms to do that. You can find that in syntax. So this is the logic behind the void setup. Logic happening behind the void setup. Initialize, like it will print some message, error message. If LoRa initialization is successful, then it will start the receiver node, and after that, it is ready for the receiving. Like it will be ready for receiving. Then you have this void loop. So this is the main thing for the receiver node. Okay. So it will keep networks connections alive. So it will check for Wi-Fi connection, like whether nothing happened to Wi-Fi and MQTT. If those connections are lost, it will try to reconnect it and ensure the device stays connected to the internet and MQTT browser. And it will also check for a new LoRa packet. Okay, it will check for the whether a new LoRa packet is received or not. If it is yes, then it will go to step 3. So what the step 3 do is, okay, it will clear a packet flag. I mean, like there is some internal syntax. It will clear that. So just leave this for now. And after the packet is received, it will handle that LoRa packet, and it will extract the useful information, GPS coordinate, speed, timestamp, tracker status, and everything. Then it will publish the data. Okay. I mean, everything is done with the previous functions used before. I mean, we created those functions, right? Handle LoRa packet, send LoRa packet, and all those things. Maintain MQTT. It will use all those functions in this. Then it will start listening again. Yeah, this loop will be going like it will repeat. It will every time repeat until you turn off the power. That's it. I'll show you the code also. You'll understand that with code better. So this is your setup. You will set up your Wi-Fi, MQTT, LoRa, and everything. And void loop, you will maintain your Wi-Fi, you will maintain your MQTT, and if LoRa packet is received, then like it will check whether the LoRa packet is received or not. Once it received, it will make that false so that like in the next iteration, it won't it won't send the same packet again. Okay. Then you will handle LoRa packet. I mean, this function will make the GPS data into a structured format, and the received data into structured format, and will publish to the MQTT broker. And this logic will, I mean, restart the LoRa receiving part. Okay, and it will wait for some time and again continue the loop. So this is the logic behind the tracker, sorry, the receiver node. And now, I mean, we are done with the firmware of tracker and receiver nodes. The only thing which is left is dashboard creation. Okay, so I'll show you how the dashboard looks like. I'll just show that. I'll first open that and I'll show you. Sure. I hope you can see that. You can see that in screen. So this is how the final dashboard will look like. So we'll have many things. The name, GPS tracker, the connection status. So it is saying that connecting since our receiver node. I mean, we are not like we don't have the receiver node right now, so it will show just connecting. Once connected, it will show it as connected. You'll have the live position status, latitude, longitude, speed, satellites, timestamp, the signal strength, LoRa signal strength, and these are some UI tools to control the location. I mean the visibility of your target. And once the connection is established, you can see a clear screen. And we will simulate this in the last part of our session. Like, in next 10 minutes, I'll simulate this. Let's go back to slides now. So now let's go back to slides. I'll share your input. Yeah, I hope you can see the screen now. So I'll explain like the logic behind this dashboard creation. We are not discussing the syntax because you need to know many basics. I mean, many different concepts like HTML basics, CSS, MQTT, leaflet, and client, several concepts. So we are not discussing the syntax here also. So instead, what I'm going to do is I'll just explain the logics. Okay. So first of all, what is a dashboard? I want to tell you what is a dashboard. So the dashboard is the final user interface of our tracking system. Its purpose is to receive tracking information from the device and display it clear real-time format. Okay? And HTML, like HTML is nothing but it creates the visual components of a dashboard, like cards, buttons, excuse me, such as cards, buttons, status indicators, logs, and then map everything. So it's like a structure, okay, structure of your dashboard. We'll use this language to create our structure. Then CSS, so it's appearance. So it's uh, like it will maintain the beauty of our dashboard. Okay, like the font size, the colors, the animations, and everything. That will be done through CSS. Then JavaScript is JavaScript is used to connect to MQTT broker to maintain your GPS marker on the map, like everything. Okay, it makes the dashboard more interactive. We'll use this language for that. It connects to MQTT broker, receive tracking data, update information cards, and move the GPS marker on the map. That's it. So basically we'll use these HTML, sorry, CSS and JavaScript for creating our dashboard. Okay, so it needs some information like prerequisite is like HTML basics and all. We are not discussing the syntax part. Directly we'll go through the logic. Okay. So what happens when the dashboard opens? First, it will load the page. It will create your HTML components. It will create the structure. Then it will load CSS components. It will create the styling, and it will try to this JavaScript will connect to the MQTT, and it will create the leaflet map. So it's a leaflet map is basically a software. It's an open source software which will uh, give you this map data, like Google Maps. It's another thing. It's an open source which will access the real-time map information and all, like villages, mandals, states, and all information. Then it will create an MQTT client. It will connect to the broker, and it will subscribe to the topic, and it will show the information. And this, like, what is this MQTT is? I hope you all know this. Like, this is taught in day 4, like session 4. So it's a message queuing telemetry transport. It's a communication protocol. It's a lightweight messaging protocol designed for IoT devices and low bandwidth networks. So basically, it will have in 3 different parts: publisher, MQTT broker, and subscriber. So publisher will send the data. I mean, the receiver node is a publisher. Broker is the Hive MQ. It's a broker. The name of the broker is Hive MQ. It routes the data. It's a broker. And the subscriber is the one. Subscriber is our dashboard. Okay. In this case, the subscriber is our dashboard. It will receive the data. And what is this message processing logic? So once the message is arrived from IMQ, what happens? So once the message is received, on message arrived, what happens is a special callback function is called And like whenever a new message is arrived, some functions will be called, and it will, it will receive that information. Okay. Then the packet arrives as plain text. So basically, this that that packet arrives as plain text. It will contain all the information, and we will extract that data and convert into JavaScript variables, and it will update. And it will update everything. Like for updating everything, it will extract the data into latitude, longitude, speed, timestamp, device status, and all those things. And there is some internal algorithm which checks whether the information is correct or not. There is okay, whether the information like the coordinates, uh, the speed, like everything is correct or not. There is internal algorithms for this, and then it will update it on the screen. Okay, the dashboard update logic. Okay, one like how it will update it. Okay, so once a new packet is received, it will parse the GPS data. I mean, it will extract that data. Okay, it will extract everything. It will update the information cards. So it will update this latitude, longitude, speed, and timestamp. It will update the status indicators. I mean, display the current tracker state such as moving, stopped, or connected. It will move GPS marker. So we will show you this. I will show you this simulation after this slide. Like at the end of the session, I will show you that. It will update the route history. So it will do that. Update the signal metrics like the signal quality and all. Update the event log. So I will show you all these things in the like after this, and it will wait for the next packet. So this loop will be you know, continuously happen. That is how the dashboard will be updated. And yeah, like okay, like we have done like most of the learning part of our project. So this is, I mean, these are the logics behind like the tracker node, receiver node, and the dashboard creation. Like since we are done of the most of the learning, the only major task which is left is PCB designing, which will be done on session 6, which is going to hold on 28th. Uh, for now, I'll show you a small simulation. Give me some time, and like this is the last part of our like today's session. Yeah, meanwhile, you can scan this for attendance. I'll just establish something for simulating, like showing the simulation part. Give me some time. Until then, you just scan this for attendance. Give me some time. Problem. sorry for sorry to say this. Like I'm having some problems with my VS Code. Cannot simulate this. We will share how to we'll share something in the group. Like after the session, you can simulate with that because I'm having some issues with my VS Code. It's not working properly. I will share some I'll share some instructions in the group. You can simulate with that. Uh, Sorry to say this. And yeah, like the session is done. If you're having any doubts, you can ask. Yeah. If you're not having any doubts, you can just scan this attendance and can leave. Thank you. Yeah, yeah, yeah. It's session 5. I think it was a mistake, but it's session 5. Tomorrow you will design the PCB. There you will know like how much money it will take for everything. Like in the tomorrow sessions, we'll get to know about everything. I mean, tomorrow you're going to design the PCB for this circuit. Okay, that session is really interesting. I mean, yeah, definitely attend that also. Thank you.